An array is the most fundamental data structure, storing elements in contiguous memory locations. It provides O of 1 constant time access to any element via its index, but its size is fixed at creation.
Dynamic arrays, like Python's list or Java's array list, solve the fixed size problem. When the array fills up, it automatically allocates a new, larger block of memory, typically doubling the capacity, and copies the old elements over. Singly linked lists consist of nodes where each element points to the next. Unlike arrays, they don't require contiguous memory, allowing for efficient insertions and deletions without shifting every other element in the structure. Doubly linked lists add a previous pointer to every node. This enables bidirectional traversal and easier deletions of a known node, though it increases the memory overhead per element.
A stack is a linear structure following the last in, first out principle. Think of it as a stack of plates. You only interact with the top item, which is how your browser manages its back button history.
Queues operate on the first in, first out principle. The first element added is the first one removed, making them essential for managing shared resources like printer tasks or CPU thread scheduling. Unlike arrays, linked lists store data in non-contiguous memory locations. Each node contains a data value and a pointer, or reference, to the next node in the sequence. This structure allows for highly efficient insertions and deletions. You simply update the pointers of the surrounding nodes without needing to shift any other elements in memory. Doubly linked lists add a previous pointer to each node. This enables two-way traversal, making it easier to move backward through data at the cost of slightly more memory per node. Moving to nonlinear structures, trees represent hierarchical data. They start at a single root node and branch out into parent-child relationships, ending at nodes with no children called leaves. In a binary search tree, or BST, each node has at most 2 children. The left child must be smaller than the parent, while the right child must be larger, enabling fast O of log n searches. Graphs expand this further into complex networks, consisting of vertices connected by edges. They model many-to-many relationships like social media connections or GPS navigation routes. Graphs are further classified by direction. Undirected graphs represent mutual relationships like Facebook friendships, while directed graphs model one-way flows like Twitter followers or website hyperlinks. Graphs can also be weighted, where edges carry specific values representing distance, cost, or time. This allows algorithms to calculate the most efficient path in GPS navigation and logistics. A tree is a specialized graph with a strict hierarchy. It begins at a single root node and branches downward without any cycles, making it the standard for representing computer file systems. In a binary search tree, every node has at most 2 children. Because the left child is always smaller and the right is always larger, searching for data takes logarithmic time rather than linear time. Heaps are tree-based structures used for priority queues. In a max heap, the highest value element is always at the root, allowing for instant access to the most important data point. Hash tables provide near-instant data retrieval. By using a hash function to turn a unique key into an array index, they achieve O1 time complexity for both storage and lookups. However, hash tables face a challenge called collisions, which occur when 2 distinct keys produce the exact same array index. Separate chaining solves this by making each array slot a pointer to a linked list, allowing multiple items to coexist at the same index.
Alternatively, open addressing searches for the next available empty slot within the array itself, keeping all data contained in a single contiguous block. In practice, hash tables are the engine behind Python dictionaries and JavaScript objects, providing the fast attribute lookups we use daily. While arrays and hash tables are linear, trees introduce a hierarchical structure where data is organized into parent and child relationships. The most common version is the binary tree, where every node has a maximum of 2 children, enabling logarithmic time complexity for sorted data. Building on the basic tree structure, a binary search tree, or BST, imposes a specific mathematical order to make data retrieval near instantaneous. In a BST, every left child must be smaller than its parent, and every right child larger, allowing the computer to discard half the remaining data with every single comparison. To prevent a tree from becoming a slow, linear list, self-balancing trees like AVL or red-black trees automatically rotate their nodes during insertion to keep the height minimal.
Heaps are a different specialized tree, where the root is always the extreme, either the minimum or maximum element, regardless of the sorting of the lower levels.
This makes heaps the foundation of priority queues, used by operating systems to ensure the most urgent task is always processed first in constant time.
Finally, tries, or prefix trees, store characters at each node rather than full values, enabling the high-speed autocomplete and spell check features found in search engines and IDEs.
Moving beyond hierarchical trees, we reach graphs, a collection of nodes called vertices connected by edges, used to model complex networks where any node can connect to any other. Graphs are either undirected, like a Facebook friendship where the relationship is mutual, or directed, like a Twitter follow, where the connection only flows in one specific direction. In weighted graphs, edges carry values representing costs, like distance or latency. This is how GPS algorithms like Dijkstra's calculate the fastest route between 2 coordinates.
We implement graphs using an adjacency matrix for fast lookups in dense networks, or an adjacency list to save memory when nodes have very few connections.
Next is the heap, a specialized tree-based structure that maintains a partial order, allowing for near-instant access to the most important element without the overhead of sorting the entire set.
In a max heap, the parent is always greater than its children, keeping the largest value at the root. A min heap does the opposite, commonly powering priority queues and OS task scheduling.
Moving to binary search trees, or BSTs. Unlike heaps, every node follows a strict horizontal order. The left child is always smaller than the parent, and the right child is always larger. This structure enables rapid searching. By comparing your target value to the current node, you discard half the remaining tree at every step, resulting in highly efficient O log n time complexity. However, if you insert sorted data, a standard BST becomes skewed. It loses its branching advantage and performs no better than a basic linked list, dropping back to O of n lookup speeds. To solve this, we use self-balancing trees like AVL or red-black trees. These structures automatically reorganize their internal layout during every insertion to ensure the tree height remains logarithmic. They achieve balance through rotations, mathematical shifts that move nodes up or down to keep the left and right subtrees nearly equal in height at all times. For massive datasets, we use B trees. These allow nodes to have many children, which reduces the number of levels and minimizes slow disk reads, making them the standard for database indexing and file systems.
While search trees focus on finding any element, heaps are specialized trees designed to provide instant access to the smallest or largest value in a collection.
In a min heap, every parent is smaller than its children, keeping the minimum at the top. Max heaps do the opposite, making them perfect for tracking the highest priority item. Heaps are unique because they are usually implemented using arrays rather than pointers. Simple arithmetic determines a node's children, saving memory and improving cache locality. This structure powers priority queues. It's how your operating system schedules CPU tasks, and how algorithms like Dijkstra's find the shortest path in a network. When data relationships become too complex for hierarchies, we use graphs. These consist of vertices connected by edges, representing any set of interconnected objects.
Graphs can be undirected, where connections are mutual, like a Facebook friendship, or directed, where the relationship has a specific direction, like a web link or a Twitter follow.
Beyond direction, graphs can be weighted, where edges carry numerical values representing distance, cost, or capacity, or unweighted, where all connections are treated as equal.
To store these in memory, we often use an adjacency matrix, a two-dimensional array where a 1 at row I and column j indicates a direct connection between those two nodes.
Alternatively, an adjacency list stores each node alongside a list of its neighbors, which is significantly more memory efficient for sparse graphs where most possible connections don't exist.
Choosing between them depends on density. Use a matrix for dense graphs where speed is priority, but use a list for sparse graphs to avoid wasting massive amounts of memory on zeros.
To navigate a graph, Breadth First Search, or BFS, explores all immediate neighbors first, making it the go-to algorithm for finding the shortest path in unweighted networks.
In contrast, Depth First Search, or DFS, dives as deep as possible into one branch before backtracking, which is ideal for tasks like maze solving or detecting cycles in a system.
Moving from traversal to optimization, weighted graphs assign costs to edges, which is how GPS algorithms like Dijkstra's calculate the shortest physical path between two map coordinates. When a graph is strictly hierarchical with no cycles and a single starting point, it becomes a tree, a structure where every node has exactly one parent except for the root. The most common variant is the binary tree, where each node is restricted to a maximum of 2 children, providing a predictable structure for data organization.
A binary search tree, or BST, adds a sorting rule. Every value in the left subtree is smaller than the parent, and every value in the right is larger, enabling rapid data retrieval. This sorted structure allows for search, insertion, and deletion in logarithmic time, meaning even as your data doubles, the search time only increases by a single step. You interact with trees daily. They power the document object model used to render web pages and the nested folder structures within every modern operating system. To optimize searching, we use the binary search tree, a specific tree structure where every node has at most 2 children. The rule is strict. The left child must be smaller than the parent, and the right child must be larger, allowing for O log n search speeds. Heaps are specialized trees used when you need immediate access to the highest or lowest value, known as max heaps or min heaps. This structure powers priority queues, ensuring an operating system always processes the most critical task next without sorting the entire list. When data relationships are complex and non-hierarchical, we use graphs, which consist of vertices connected by paths called edges. Graphs are undirected for mutual connections, like Facebook friends, or directed for one-way relationships, like Twitter followers or web page links.
Graphs can also be weighted, where edges carry numerical values representing distance, cost, or time, allowing algorithms like Dijkstra's to find the most efficient path.
To store graphs in code, an adjacency matrix uses a 2D array, where a 1 indicates a connection. It's extremely fast for checking if 2 nodes connect, but consumes significant memory. Alternatively, an adjacency list stores only existing connections for each node, making it the standard choice for sparse graphs where most nodes are not interconnected. It is important to remember that a tree is actually just a specialized type of graph, one that is fully connected but contains no cycles or loops. Hash tables provide near-instant data retrieval by passing a unique key through a hash function to calculate a specific index in an array where the value is stored. When 2 different keys generate the same index, it's called a collision. Most systems resolve this using chaining, where each array slot holds a linked list of multiple items. Alternatively, open addressing resolves collisions by searching for the next available slot in the array. This keeps all data within the table itself, but can lead to clustering as the table fills up.
The most flexible structure is the graph. It consists of nodes connected by edges, representing complex relationships like social networks or GPS map routes, where data points don't follow a linear or hierarchical path.
Mastering these structures is about choosing the right tool for the job. While arrays provide instant access, hash maps offer the fastest lookups, and graphs handle the world's most interconnected data. Every modern application is built on these fundamentals.